Hi, I'd like to do an example that reviews a little bit of kinematics and uses Newton's second law to talk about why it's essential anytime you find yourself falling to try and relax, and if you land feet first, make sure that you bend your knees to bring yourself to a stop. So, say someone is dropping from a window to the ground that happens to be half a meter below. Half a meter is the height of this tiny whiteboard, or possibly even a little bit shorter than that. And the person has a mass of 80 kilograms. So they're starting at rest right as they step off from this window ledge and land half a meter later. But when they land, they lock their feet and their body is able to come to rest by moving an additional distance downward of only 2 centimeters. So normally when you jump up and land, your knees bend, your hips bend a little bit, your body flexes to give you a longer distance over which you come to rest. But if that happens in 2 centimeters, how much force are we going to experience? Well, using our known-unknown concept equation brainstorming for this, if we want to figure out force, we need to be able to find acceleration, because our acceleration is our force divided by our mass. We have a mass, it's 80 kilograms, that's a known, so our force would be our mass times our stopping acceleration. Now when we look at the motion though, if we want to find the stopping acceleration, we know that we're going to end at an ultimate final velocity of 0, and we would need to know how fast we're traveling right when we hit the ground. So that means we need to look at the falling motion. So there are actually 2 motion problems snuck in here. A free fall and then the stop. So from the free fall, we're actually falling subject only to the force of gravity from rest. So for the fall portion, this first portion, our initial velocity for the fall is 0. Our acceleration is minus the strength of gravity, negative 9.8 meters per second squared, and our change in y has to be negative because we're moving down, falling from rest. So our change in y is going to be minus the height, or negative 0.50 meters. Now our unknowns for this first piece, we don't know the time it takes to fall, we don't know the final velocity of the fall. But when we find the final velocity of the fall, that becomes a known to allow us to calculate the acceleration of the stop, again without knowing time. And the family of equations for kinematics without knowing time tells us that our displacement is going to be our final velocity squared minus our initial velocity squared, all divided by 2 times the acceleration, or the acceleration is the final velocity squared minus the initial velocity squared, divided by 2 times the displacement, or solved for our final velocity will be the square root of the initial velocity squared plus 2 times the acceleration times our change in y. So, for our first part of our motion, the final velocity of the fall, our initial velocity is 0. So we have 2 times our acceleration, negative 9.8 meters per second squared, times our displacement, negative 0.5 meters. So our 2 minus signs will give us a plus sign. So we'll get a real answer here. So this problem isn't physically excluded from working. So the square root of that value is going to give me plus or minus 3.13 meters per second. But we do know that we can choose one of those 2 solutions, because if we're moving down, we would have a negative velocity. So our initial velocity for the stop is our final velocity for the fall, negative 3.13 meters per second. Step 2, our acceleration for our stop. Well, that's going to be the final velocity for our stop, which is 0, minus the initial velocity for our stop, which we just determined here, is negative 3.13 meters per second. So that negative sign gets squared away, but we also have this negative sign from the equation. So our numerator is negative. In our denominator, we have 2 divided by our displacement. Again, as we stop, we continue moving down, so our displacement would be negative 0.02 meters. So negative 3.13 quantity meters per second, quantity squared, divided by 2, divided by negative 0.02 meters, gives me a value, minus over minus, gives me plus 245 meters per second squared. 25 times the strength of the free fall acceleration. So in terms of a force, 80 kilograms times 245 meters per second squared gives me 19,600 newtons, 19.6 kilonewtons, which is about the weight of a full-size SUV. So if you watch a lot of sports, some of the worst looking injuries, you often wonder, well, how could that happen? That's part of the reason. And in basketball, some of the worst injuries you'll ever see is if someone goes up for a jump shot, gets fouled, and even though they're only falling a short distance, they land with an almost totally locked leg. Well, that totally locked leg means you take a very short distance to stop. The shorter the distance, the larger the acceleration that you have, the larger the forces acting all along your body. And particularly if you only land on one leg, then all of that force gets concentrated just over that area, which can cause some serious damage to the ligaments and bones, which is part of the reason why fouls for shooting are so heavily enforced in basketball. It's all about keeping people safe and healthy. Thanks for watching.